Hey everyone, in this section we're going to be introducing these fundamental trigonometric identities, and then in the next video we're going to show you how to use them to solve problems. So to begin, let's define an identity. An identity is an equation that is true for all variables in the problem for which both sides are defined. So this is just a formal way of saying that two things are equal to each other for every possible input for the given variable. Let's go ahead and start off with some ones that we've seen before. We saw before that when I take sine of theta and divide it by cosine of theta, which is opposite over hypotenuse divided by adjacent over hypotenuse, I get opposite over adjacent, which is tangent of theta. And by similar argument, you can find that the cotangent of theta is equal to cosine of theta divided by sine of theta. This is one of our first trig identities that we've already seen, but now we're actually going to work with it in problems. We also defined the cosecant function as 1 divided by the sine of theta, and the secant function as 1 divided by the cosine of theta. These also count as identities. So all these identities have names. The quotient identities are the ones for tangent and cotangent, and the reciprocal identities are for cosecant equals to 1 over sine of theta, or sine of theta equals 1 divided by the cosecant of theta, as well as secant of theta equals 1 over cosine of theta, or in reverse, cosine of theta is equal to 1 over secant of theta. Next, we're going to talk about these ones called period identities. Recall in a previous video that we were able to take the sine of 450 degrees and split up 450 degrees as 90 degrees plus 360 degrees. And we observed that the sine function essentially doesn't notice this full turn of 360 degrees, so we're just looking at the sine of 90 degrees, which turns out to be 1. We justified this originally by discussing full turns on the unit circle, because if I take a 360 degree turn, or a 2 pi radians turn, my corresponding coterminal angle would be the exact same location. And it turns out that this phenomenon can be expressed with all 6 of our trig functions. Before we get into that, we have to go over a couple of facts. First, the functions sine, cosine, cosecant, and secant are functions all with a period of 2 pi, but the tangent and cotangent functions have a period of pi, which is half the distance. So once we have this, we get the following period identities. So we'll first start with that first group of trig functions that have a period of 2 pi. The idea is that anytime I see 2 pi within one of these functions, it essentially vanishes, and that's what's happening with these identities. Next, we can talk about the tangent and the cotangent function, but the identities for these work as follows. Tangent of x plus pi equals tangent of x, and cotangent of x plus pi equals cotangent of x. Because these functions have a shorter period, it's all additions of pi itself that vanish. And these period identities actually do generalize. So if I let n be any integer, then I get the following representations. This is basically saying that these rules generalize for an arbitrary scalar multiple of either 2 pi in the first 4 trig functions, or just pi itself in the last 2. So if I'm looking at the sine, cosine, cosecant, or secant function, any even multiple of pi will vanish. But if I'm looking at the tangent or cotangent functions, then any integer multiple of pi will vanish. We've spoken at length about how the functions sine and cosine are periodic in nature, and it turns out every trig function is periodic, but these periodic identities are just a way of numerically observing the periodicity of all these functions. Next, we have the so-called Pythagorean identities. We've drawn this picture before when we were constructing the unit circle. And remember that the unit circle is simply just the circle of radius 1 centered at the origin. Now, if I go into the first quadrant and inscribe the circle with a right triangle, I'm going to have a hypotenuse length of 1, a horizontal length of x, and a vertical length of y. And we saw that the cosine and sine of theta is equal to x and y respectively. The Pythagorean theorem, which says that a squared plus b squared equals c squared, does apply to this triangle. It tells us that x squared plus y squared is equal to 1, which, surprise surprise, matches our unit circle equation. And this is no accident. This is definitely a very nice mathematical connection that's happening here. But the reason that we're bringing this up is that I have an identity between x and cosine of theta and y and sine of theta. I'm going to take my equation x squared plus y squared equals to 1, and I'm going to substitute x for cosine of theta and y for sine of theta. When I do this, I get the equation cosine squared plus sine squared is equal to 1. And it turns out this equation is always true. If I plug in any angle for theta that I want, taking the cosine squared and adding the sine squared of that angle theta will always give you the number 1. This is known as our first Pythagorean identity, which conventionally is expressed as sine squared theta plus cosine squared theta equals to 1. And I'm using identities here in the plural sense because I have two more. And they're very easy to derive. All I'm going to do is play around a little bit with the algebra. The first thing I'll do is I'll take our first Pythagorean identity and divide both sides by the sine squared of theta. When I go through the algebra and simplify, I get our second identity, which is 1 plus cotangent squared of theta equals the cosecant squared of theta. In a similar manner, if I take the first Pythagorean identity and divide both sides by the cosine squared of theta, then I'll end up with the third Pythagorean identity of tangent squared theta plus 1 equals to secant squared of theta. Now, if you've seen trig identities in another class before, it's likely that you had to memorize all three. But the Pythagorean identities are very nice because I only need to remember the sine squared theta plus cosine squared theta equals to 1 identity, because I can just derive the rest by dividing both sides by either sine squared theta or cosine squared theta. The last set of identities that we'll look at are the cofunction and even and odd identities. First, let's recall what the graph of sine and cosine look like. Now consider the function sine of x plus 2 divided by pi. This is a sinusoidal function with a phase shift of negative pi over 2. This means that I'm going to take the sine function and shift it to the left by pi divided by 2 units. When I do that, it actually turns out that I get the exact same graph as the cosine function. In other words, I've established the identity cosine of x is equal to sine of x plus pi over 2. And I'm not going to draw graphs for each and every one of these, but I can think about it in a similar manner that taking any trig function and shifting it to the left or to the right by a sufficient amount will give me a matching other trig function. So those identities are expressed here as follows. So sine and cosine are related by a horizontal shift, cosecant and secant are related by a horizontal shift, and tangent and cotangent are related by a horizontal shift. And last we have the even and odd identities. The first set of identities, which are going to be our odd identities, essentially say that these four trig functions, whenever I'm evaluating them at a negative value, that negative sign can factor out front. Our next two identities are called our even identities. The cosine and secant function essentially don't notice negatives. If I look at cosine of negative x, it's the same thing as cosine of positive x. And the same thing happens with the secant function. So basically, the identities on the left say that whenever I'm plugging in a negative value to one of these four trig functions, that negative sign factors out to the front. But my two functions to the right, cosine and secant, whenever I'm inputting a negative value, I might as well have just inputted the positive value because these functions can't tell the difference. Think about the function f of x equals to x squared. If I plug in a positive 2 or a negative 2, I'm still going to get the same output of 4. And this is true with any even and odd pair of numbers. This is what it means to be an even function. Alright, well thank you so much for watching. In the next video we're going to talk about how to apply some of these identities. And even though there are a lot of identities here, which can be a little daunting to look at, the expectation is not that you have to memorize them, especially for homework. You're going to have them listed out in the notes for you, and you can take screenshots of these slides if you want, because it's good to have them as a reference and practice using them.